the merge sort. In an episode dealing with the merge sort, you might expect that we would describe the merge sort algorithm. However, I would not do it because it's simple and we would practically waste our time. What I would like to focus on is on specific aspects of the merge sort. So I want to begin with the first aspect, specific aspect of merge sort, specifically those that are not discussed in standard episodes about merge sort. So let's compare the merge sort to the selection and the insertion sort. So we know that in the selection and the insertion sort, those are one of the naive algorithms for sorting, and they take an asymptotic type of O of n squared. The merge sort takes O of n log n. However, there is a disadvantage also in the merge sort because its constant time factor is higher than the selection and the insertion sort. This is because we have many operations inside the merge sort. For example, we need to copy all the items into new arrays. We don't do it in place. So the constant factor is higher. So if you have a very short array, it might well be the case that insertion or selection sort would run faster. If you have an asymptotically large array, then the merge sort would indeed take a major less amount of time because it's asymptotically much less. It's O of n of log n, which is also called a linearithmic time complexity. The merge sort also, the differences in between it and the selection and the insertion sorts and all the like, is that it does not work in place, which means when we split the array into two and then we tell each of the parts of the array, hey, you take this first part of the array and sort it recursively, and you guy take the other part of the array and sort it recursively, then we don't do this in place. We actually do a copy of the two arrays and we let them sort it. We'll discuss why we don't do this in place in another item. You can take it as an exercise to try and sort it in place, and you see you will face many difficult problems which would hinge you from doing this in an asymptotic time of O of n log n. In the merge sort, the basic thing that we do is that we recursively sort the first byte of the array, then the second byte of the array. The pointers, the way I would like to do this is to start from 0 into the middle and then take the middle plus 1 into up to the end. And then you do the merge. When you call the merge method, then you have to pass all the indexes and the sub-arrays that you're going to sort. So basically, if you look at the merge sort, then what you'll see intuitively is that it's doing divide, and then another divide, and then another divide, and almost no work is happening during the divide process. It's only dividing and preparing the arrays. So you do a divide into two, and then you do divide each part into two, and then you divide each part into two until you reach specific arrays of one item. The main point I want to emphasize here is that you can see the merge sort as a two-step process when looking at it like 40,000 miles ahead. The two processes are the divide and then the merge. So there is divide, 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 divide until we get a single item in each array, and then merge and merge and merge and merge until we get the original array only sorted. So I think this is a very useful way of looking and understanding recursion algorithms in a way where you go deep and deep and deep and deep until you get to the end, and then you start doing the actual process. Because during the divide time, we don't do really any processing into the arrays. It's only in the merge time that we actually do the merge, the sorting. This is where all the work goes into. And now to the point of why don't we do the actual work and the actual sorting in the merge sort in place? Why do we split it into duplicate and we actually clone the subarrays when you split the array into two, and when we merge them, why do we clone them? The reason is that if you wanted to merge and to sort the two halves of the arrays, then you would practically need to shift items. shifting items inside the arrays would mean you would get into of n squared. So it's pretty much a must to use clone arrays in the merge sort, and this is where the constant time additions come into place. This is basically the main algorithm. We do create temporary arrays in order to do all these merges and to merge them back into a single array. And now I want to stress out another point, because when we do the merge of two arrays, let's say I tell you, because this is the assumption in a merge sort, that we have two separate sorted arrays. So let's say I tell you I have two separate sorted arrays and I want to combine them into a single array. The straightforward way to do this would be to take the two arrays and compare each item from the first item for the first array and the first item from the second array, compare them. If the first is smaller, we copy it into a new array, and then we compare the second item in the first array and the first item in the second array. However, there is an edge case here, which is if we get to the end of one of the arrays, then we know for sure that all the items in the first array are smaller than all the items in the second array. However, we need to make sure that in our conditions, we do not have an index out of bind, because if you only do the comparisons and you increase the index on the first array and the index on the second array by 1 each time, then what you'll face is an index out of bound. This leads us to checking in a condition whether we are not out of bound of one of the arrays, and if we are, then all we need to do is to continue and copy the other array, because we know that we already fetched all the items from the first array into the merged array. There is a trick here, and a great one. What we can do is, in order to avoid all these conditions, because adding all these conditions about is this item smaller than the item on the second array, and whether I have reached the end of any array, can we get rid of any of the conditions? More specifically, can we get rid of the condition of whether we reached the end of the array? And the answer is yes, we can get rid of it. What you need to do is this. When you split the array into a 2, then you add another item at the end of each subarray, which is infinity. And then you are sure that infinity is going to be greater than any item on the other array, which makes it strictly that when you compare two items, then when you reach the end of the first array, you will start getting the items from the second array until the end. And with this trick of when you split the array, you add another extra item to each of the sub-arrays, which is infinity, then in this way you are avoiding any need to compare whether we reached the end of the array. And because we know the size of both of these arrays, so our loop will only scan all the items until the infinity. And with that we avoid the additional condition. So this is a very nice trick. Whenever you need to merge two arrays, what you can do is append infinity to the end of each array, and with that you would be able to avoid an extra over complex if condition that would check if we reach the end of any sub array. And this is great. This would make our if condition much simpler. And now to the time complexity of merge sort. So you might have already noticed that the time complexity is of n log n, also called a linear rhythmic time complexity. Because if you take the function that measures the time complexity of merge sort, what you would see is that you split the array into two, and the time complexity of the whole thing is the time complexity of half of the array, plus the time complexity of merge sorting the other half of the array, which is twice the time complexity of merge sort on each half of the array, plus you need to merge them. This is some function of n, which goes over all the n items and merge them. Which means that T of n, the time complexity of merge sorting, n items is twice the time complexity T of n divided by 2. Twice the time complexity of doing a merge sort on each sub-array plus the time complexity needed to merge the two arrays. The issue here is that we have just defined the time complexity of merge sorting the whole array in terms of its own time complexity. So we have a recursive time complexity definition, and this leads us to practically nowhere. Because if you solve a problem in terms of its own problem, then you didn't really solve anything. If you look for definition in the dictionary, you don't expect to find the definition of a word in terms of its own word. And this is just what we did, because we said that time complexity of sorting n items is the time complexity of sorting half the items twice plus the time complexity of merging these two twice of items. What comes to save us is the master method. The master method is a formula that you can just remember, which says that if you have an equation of type time complexity of n is equal to a times time complexity of n divided by b, all this plus some function of n, then you know that the time complexity of t of n is n log n. Okay? So the basic formula whenever of the master method just tells you it's a given. You can prove it, it's a given. That time, if you ever happen to come across to calculate the time complexity of doing an operation on n items, and you would see that the result of this formula, some constant a times t of n divided by some other constant, it can be the same, divided by b, plus some function of n, then it's a given that this time complexity is O or even theta of n log n. So to repeat, whenever you solve an equation of time complexity of t of n, which is equals to a times t of n divided by b plus some function of n, then you can in half a second say the time complexity here is linear arithmetic, theta of n log n. So I hope you enjoyed this episode. If you have any comments or suggestions, just write them on the comment section for the podcast. Be it on Apple Podcast or wherever you consume your podcast. Thank you for listening, and I will see you on the next time.